All right, thanks. So thanks for inviting me out. Yeah, so I'm going to tell you about how we can do ab initio reconstructions with SAXS or even SANS data. So there's a host of different modeling types out there, right? So there's just direct structure fitting, where you take an atomic model and you use Kreisel or Fox or something like that to calculate a scattering profile and see if it fits. And then there's ab initio reconstructions, which allow you to determine the shapes of models. I'll talk about both bead modeling, and which is from the BioSAXS group primarily, and I'll talk about my own software called Dense for doing that. And then there's all the rest of these, which are more advanced atomic modeling methods mostly, that allow you to throw in, just like Dina was just explaining, allow you to throw in a whole bunch of different types of information to get much more of a hybrid integrative modeling type approach. So I'm going to tell you about the ab initio 3D reconstruction process. So I'm kind of going to break this up into two parts, where the first part is going to be sort of just explaining how these methods work. And then the second part, we'll actually go through a raw tutorial, as McCall was mentioning. So over the last several decades, there have been a variety of different approaches that have been developed for attempting to generate three-dimensional models from scattering data. So one of the earliest approaches was really just simple shapes, where you would take a simple shape like an ellipsoid or a cylinder or a core shell or something like that, and you assume it's a homogeneous uniform density defined by this envelope of this shape. And you refine the parameters of this shape, the axial ratios and the overall size dimensions and things like that. And you calculate the scattering profile from that shape, and you refine those parameters until it best matches your experimental data. You can also do this with collections of simple shapes. And then there was the advent of using spherical harmonics to define these shapes. And this way you got much more complex shapes, but there were still a lot of implicit assumptions, primarily that it was uniform, homogeneous density. But there were a lot of issues with this. You can't get cavities, and the shapes could only be so complex, things like that. One of the things that really caused SAXS to take off as a general tool for the user community was the advent of bead modeling. And this is where you can actually define the object as a bunch of uniform beads, where they're all the same size and shape and generally all the same distance from one another on this kind of lattice grid. And you turn beads on and off, and you figure out which configuration of beads gives you a scattering profile that best matches your experimental data. A lot of people think of bead models when they think of SAXS data, to be honest. So it's become extraordinarily powerful as a way of only using the 1D scattering profile to give you a three-dimensional shape. And then, of course, we have hybrid modeling, which, as I said, is throwing the whole kitchen sink at this, everything that you know about your system to get a high-quality atomic model that agrees with your SAXS data, as well as the remainder of your other types of data. So all of these approaches I would put under the heading of modeling. And what I mean by that is you're generating lots of different candidate atomic models or coarse-grained models of some kind, and you're calculating scattering profiles from them, and then comparing them with the data and optimizing those parameters or those models so that it best matches the data. You're generating sometimes millions of different candidate models to be able to do this. So those are all the modeling approaches, and I'm going to talk about an approach I've developed, which is the approach known as Dense, which allows you to actually generate electron density directly from the scattering profile. It's the first way of actually solving the inverse scattering problem, where you're using the intensities and having it directly tell you what the electron density function itself is in 3 dimensions. So first I'll talk about bead modeling. I'll focus today on how we do bead modeling and how we do density reconstruction, as those are the two most common ab initio reconstruction approaches. So any kind of modeling, be it atomic modeling, bead modeling, or anything, requires you to be able to calculate scattering profiles from atomic models or from whatever your model is. This is a very non-trivial problem, right? While there are equations such as the Debye equation here, which allow you to directly calculate a scattering profile from a model, this is an overly simplified view. There's a lot of considerations that go into this: how you deal with solvent, how do you actually change the model in order to calculate the next sort of iteration in your updated model. how you deal with excluded volume, how you deal with hydration shells, how you deal with the form factors of atoms, all these different types of things. So there's a lot of consideration that goes into it. And because you're using so many models to generate all these scattering profiles, it has to be fast. And there's always these trade-offs between various algorithms for speed and accuracy. There's molecular dynamics, there's implicit solvent, explicit solvent. All of them effectively boil down to a few different variations on this Debye equation. It could be the direct Debye equation, it could be spherical harmonics or Zernike polynomials or something like that. But they generally all boil down to some form of the Debye equation, some form of spherical averaging of the intensities. So I'll start with ab initio bead modeling. So there are a lot of different bead modeling algorithms out there. The most common is probably DAMMIF or DAMMIF, and this is part of the ATSAS package of programs. And the way these work is you effectively fill a grid in one way or another. Fill a grid, it's sort of this hexagonally packed sphere packing lattice. And you turn beads on or off. They can either be solvent or particle. And you turn beads on or off, and you calculate the scattering profile from whatever that collection of beads is. And usually it starts with a random configuration. And as you turn beads on or off, if adding that bead to the particle improves the quality of the scattering profile, you keep it. And if it makes it worse, you reject it and you move forward. The problem with this is that there's really just too many possible configurations of beads that you just can't calculate that many. So you can't cover this whole conformational space in any kind of time scale that we can utilize. So they use Monte Carlo approaches to do this, where they're randomly moving and selecting beads to change. Problem with these is that they fall into local minima. And so they use simulated annealing to attempt to find a global minimum. But of course, you'll never actually find the true global minimum because it's just too many different options, not only from a computational point of view, but also from a fundamental point of view in the fact that you are attempting to represent the three-dimensional particle using a one-dimensional scattering profile. So there's always going to be this issue of uniqueness and degeneracy when you're doing this. There will always be many different bead models that give you the same scattering profile effectively within the noise. One of the big things that you have to be careful of, and this goes with any kind of SAXS modeling, and particularly with ab initio modeling, is that there's a large risk of overfitting, and so you want to avoid overinterpreting envelopes in this process. So the most common software I mentioned is DAMMIF, so I'll just talk about this briefly. So DAMMIF uses this bead modeling approach in order to optimize this chi-squared fit, right? Where you have the calculated scattering from your model and the difference versus your experimental data, and you divide that by your errors. And you sum that over all your data points. Except DAMMIF doesn't only use the chi-squared as your driving score. And so what it does is they develop the score function where, in addition to the quality of the fit to the data being minimized, chi-squared, they also have these penalties. What they realize is that if you just allow chi-squared to be the only driving scoring factor in generating these envelopes, they get these models that are sort of disconnected. They have like beads scattered. And we know certain things about particles. Things like proteins are long connected objects, and they fold up into globular shapes. So they can use this information to make sure that the particles that are reconstructed by these bead models are actually connected to each other. So these penalties like connectedness or looseness are these different criteria for additionally weighting this scoring function in order to come up with a model that not only fits the data, but also agrees with these compactness features that we know to be prevalent among most particles. As I mentioned, we use these programs use simulated annealing. And so running this multiple times, you'll start with different random configurations, and it gives you different answers, slightly different answers each time. And so when you run this with the same data, and you run it multiple times, and you end up with multiple different models, all of which equally agree as well with the scattering profile. And that's simply because of the degeneracy of the scattering data, right? There's only so much information in a scattering profile, and you're attempting to reconstruct a 3D model using that 1D data. So what people do is they actually run it multiple times, and then they come up with what they call a consensus model. So the program DAMMIF is what's commonly used to effectively align all of these different bead models to each other, and then select which beads are common among all of these different models. And you come up with a single bead model that looks most like the rest of them. It's kind of like averaging, but it's not quite averaging because you're still dealing with beads. It's either on or off. And typically you'll run 10 or 15 models and do this averaging. And this works quite well. Over the last, I think this was published, the original bead modeling was published in like 1998 or something like that, right? So this has become very popular because it's a relatively robust way of getting an overall shape of your particle just from the 1D scattering data. So you can see here a series of different examples where we have the bead model shown in this transparent envelope and the atomic structure here, and also these other ones as well. And one of the nice things about SAXS is because SAXS is low resolution and in solution, you can actually get some information about the dynamics that wouldn't necessarily be resolved in a crystal structure, because if it's moving even just a little bit in the crystal structure, that disorder will result in a lack of electron density in your crystal structure reconstruction. So the ab initio bead modeling will allow you to actually reconstruct some of those dynamics. All right, so that's a brief overview of how bead modeling works. And now I'm probably going to spend a little bit more time on dense, since this is what I do. I know far more about dense, and so I can give you some more details on it. So dense is a way of reconstructing three-dimensional density directly from the 1D scattering profile. So this is a fundamentally different approach than bead modeling, and really any type of modeling, because all other types of modeling solve the forward scattering problem, where you generate models, calculate the scattering profile, and minimize those parameters in order to optimize that scattering, that fit to the scattering profile. But dense actually solves the inverse problem. What dense does is it actually uses the scattering profile to tell you what the 3D density actually is supposed to look like. And there's a lot of advantages to this. One is simply that you're reconstructing actual density. So it's a continuum of values as opposed to just beads which are on or off. It's not just a shape, it's actual density. So there's a lot of advantages to this. So how do we do this? How are we able to actually get a three-dimensional density from a 1D scattering profile? Well, we kind of have to think about this in Fourier space in order to understand how this works. So if you take an electron density function of a single particle, I think we have lysozyme here, you do the Fourier transform of that, and you get what we call the molecular transform, which is the Fourier transform of a single particle. Okay, and so it's this continuous distribution of effectively structure factors from the point of view of crystallography of these Fourier terms, with amplitudes and phases at each point in this what we call reciprocal space. Okay, so we're looking here at the intensities in reciprocal space, which are the amplitudes squared. You notice there's a big blob of intensity in the middle, and as you get further and further out, it gets weaker and weaker. And this is the source of the SAXS signal, right? At small angles or near the origin of this space, we have a lot of intensity. We can see that signal. But as we get further and further away from the origin of reciprocal space, that signal gets weaker and weaker in these wider angles, or the wax regime. Now, what happens is that if you were to take a two-dimensional cross section through this, you would actually get what you would see if you could do a single particle diffraction experiment. You'd get something like this. It would be a cross section through this three-dimensional molecular transform. And you can see that blob of SAXS signal in the middle, and then it gets weaker as you go out. So in single molecule imaging, you can actually do some level of single molecule diffraction nowadays with SIBYLS, though it's very early on in its development. You have to solve what's called the phase problem, right? You can measure the intensities, which tells you information about 3D amplitudes, but it doesn't give you any information about the phases. So you have to solve the phase problem. The other problem in terms of solution scattering is that we don't get these nice, fancy, high information content, continuously fluctuating scattering profiles on our 2D detector. Because the molecules are all randomly tumbling in solution, these patterns are all randomly oriented in reciprocal space, and then you add that up over millions of molecules, and it all averages out. You get this spherical averaging, we call it. And so now you just get a function of intensity as a function of your Q, or your angle on the detector that you're actually scattering to. So not only do we have to solve the phase problem, we actually don't even know the 3D amplitudes, right? So not only do we have to solve the phase problem, we have to solve the whole structure factor problem, where we have to determine both the 3D amplitudes and the 3D phases in reciprocal space using just the 1D scattering profile. And this is the problem that DENSE solves. So we call this iterative structure factor retrieval. It's very similar to iterative phase retrieval, which is what single molecule diffraction people in the coherent diffraction imaging world use to solve the phase problem when you know the 3D amplitudes. Here, we're doing something very similar, but we don't have 3D amplitudes, right? We only have one-dimensional spherically averaged intensities, but it's a very similar process. So what we do is we start in the upper left with completely random density. So we're showing a grid here, right? A grid of points. And this grid of points is how you tell a computer what electron density is. It's like a three-dimensional image, right? And so there's pixels, right? Just three-dimensional pixels that we call voxels. And each one of these pixels or grid points has a value or a density associated with it. And then your viewers like Chimera or Pymol are actually just viewing that in this fancy interpolated graphical program. But ultimately what it is just this grid of points. So you assign each one of these grid points a random number to start with. And then you calculate a forward Fourier transform, and that gives you a similar grid of points, but now these points are in reciprocal space. This is the molecular transform of your initial random density, right? And so what happens is you know that these structure factors should theoretically have a corresponding scattering profile that matches your data, but of course it doesn't because we started with random density. So we need a way of changing these structure factors such that they have a scattering profile that matches your density. So that's exactly what we do. First, we calculate from these structure factors in 3D, the three-dimensional amplitudes, right, which is just the amplitude squared. So we get this three-dimensional amplitude grid. And then from that, we calculate the spherical average. So we bin all of these grid points into spherical shells, and then we can calculate the average of all of the intensities within each shell to give us a one-dimensional scattering profile as a function of the Q vector, right? Whatever the radius of that shell is effectively our Q vector. And what we know is that the scattering intensities of our model here should have a spherical average that matches our experimental data. So what we can do is we can scale the structure factors such that their corresponding intensities have an average that matches your data. That's effectively what DENSE does. That's what this structure factor retrieval algorithm does. So you, for example, let's take this QJth shell here. We have all these grid points in here, right? So we have, I don't know, 10,000 grid points in this shell or something like that. And we have one data point to determine what the scale factors for all of these grid points are. But we obviously don't have enough information. So what we do is we determine the scale factor that would scale our experimental data up to our calculated data, right? And what this allows us to do is determine the scale factor for the entire shell. So we actually use one scale factor, and we scale all the grid points within this shell by the square root of the ratio of the experimental to the calculated data. So we scale the structure factors, and we use the square root of this scale factor because we're doing structure factors rather than scaling intensities. So now we scale all of the structure factors within each shell by that same scale factor. And then we do that for each one of those concentric shells. And this gives us a new set of structure factors whose 3D intensities now have a spherical average that matches our scattering profile. Now, the problem with this is that when we do this, we get now a structure factor, a set of structure factors that agrees with our data, but that doesn't necessarily mean it's correct. It just means it agrees with our data, right? So what we do is we calculate the inverse Fourier transform to bring us back into real space. And this gives us an initial very noisy density function, right? And the reason it's so noisy is because even though the average of the amplitudes or the average of the intensities is correct, the problem is that the distribution of those densities is very unlikely to be correct because we started with random numbers. So we have to do something to improve this. And this is where the real space constraints come in. So in real space, we actually know some information. For example, we know the particle is a finite compact object. We know that the density is likely positive, right? So we can use this information to flatten the solvent, right? This is exactly what we do in crystallographic density modification. We do things like solvent flattening. So we do solvent flattening, and that takes us to sort of a cleaned up density map, right? We get a blob of density somewhere, and it cleans up the rest of the density in the solvent. But this only gets us a little bit closer. So we have to iterate through this process maybe a few thousand times until we converge to a solution that gives us a nice high quality density map that agrees with our data. So this process of solvent flattening is an important one. This is our primary real space restraint. And we do this through an algorithm known as shrink wrap. So shrink wrap takes our initial noisy density, calculates a low pass filter, which is effectively just blurring it out. And then it looks at which grid points are above some threshold. And we typically take that threshold to be like 20% of the maximum of this grid. And then that defines what we call the support or the envelope of the particle. And then we flatten all of the solvent outside that envelope, and we allow the density to be retained on the inside. And that's how we determine our solvent envelope. So you can see this process here in this animation. Again, we start with random density on the top. The calculated scattering profile for that random density is in the red dots on the bottom left. And we have our experimental data in the black dots. But rather than using the actual experimental data, we use a fit to the experimental data using something like an indirect Fourier transform, like GNOME or something like that. And that black curve there is what we're actually fitting. And then on the bottom right, we have chi-squared just as a metric of that fit. And you can see that almost instantly it converges to some kind of globular object, right? And then every 20 steps or so, as the density improves, we update the envelope with shrink wrap. And we're continually sort of chipping away at this envelope. You can kind of see it chipping away. And over time, we get more and more density on the inside and less density in the solvent until ultimately it converges to something that looks like our particle. And so you can see here, we can just dock in for comparison what the known structure is. Now you're starting with random numbers and you only have your 1D scattering profile. And so every time you run this, just like with bead modeling, you're going to get a different reconstruction. But it turns out that those reconstructions are pretty much just fluctuations of this higher resolution density. But at low resolution, you're getting a very similar reconstruction. You kind of see that here. So in each case, this is a different object here, but in each case, we're seeing these variations in the higher resolution features, but overall, the low resolution globular nature of the particle all agrees across these different reconstructions. So you run this something like 20 or 100 times, and you align them and you average them to produce your final density. And then if you want to, you can further refine this. That process of alignment and averaging also allows you to estimate resolution. And so you can actually compare how well all of these different reconstructions correlate with the final answer. And that gives you an average Fourier shell correlation, just like we use in cryo-EM. And that can be used to estimate resolution, which is typically on the order of between 20 and 40 angstroms is the typical resolution. It depends on the size of the particle. Density also has the ability to impose symmetry. We have both cyclical and dihedral symmetry in here. And so we call it NCS for non-crystallographic symmetry. We use similar procedure as crystallographers, where we take the object, we define the axis of rotation as being one of the three principal axes of inertia of the object, which you're allowed to choose. A lot of times you can't do that in most programs, but in DENS you can actually choose which axis you would like to apply the symmetry around. And effectively what you do is just rotate it, right? If it's a threefold symmetry, you know you're supposed to rotate it 120 degrees. So you do that, and then you average it, and it works pretty well. So here's an example of a very difficult to reconstruct particle. It's an immunoglobulin. It's pentameric, so it's got a 5-fold symmetry. You can see without that symmetry, it does a really bad job of reconstructing this simply because it's just a really difficult shape to reconstruct. It's very disc-like, which is really hard for ab initio programs. But it's also got a lot of features. But once you apply 5-fold symmetry, it's able to give you a very good reconstruction. This is just one reconstruction, not an average. But not only is it giving you that 5-fold symmetry, you can see generally the features that you're looking for and even the hole in the middle. And it's also overall, it's got that flat disc-like shape that you're looking for. One of the major advantages of using density is that there's no restraint on being a uniform density, which is pretty much all other ab initio modeling programs assume a uniform density. So this means that you can model different particle types. Right now, for proteins, sure, uniform density is a very good approximation at low resolution. But other particles, like particles that contain lipids or detergents, often have negative contrast, right? So you get your particle density, but this is all relative to the solvent. And so some parts of the particle, like the detergent or lipid tails, will have lower density than the actual bulk solvent itself. So it'll actually have negative contrast. And regular programs cannot model that, right? If you try this with bead modeling, it generally fails because it's assuming it's all uniform density. So you can actually just remove the positivity constraint in dense very easily to allow for this negative contrast and reconstruct membrane proteins, or in this case, a nanodisk or a micelle or something like that. We call this membrane mode. You just type -MM and it works. It works quite well. And this effectively just means that it's relying solely on shrink wrap and solvent flattening to be able to reconstruct the particle. And since all you're really doing is removing that positivity restraint, you can work with any particles. It doesn't have to be membrane proteins. So people have done this in material science applications for like particles and toluene and stuff like that. So that works really well. And it also helps with working with SANS data out of the box. There's no form factors of atomic models or coarse grain beads or anything like that. It's just Fourier transforms back and forth and solvent flattening. It's a very, very simple approach. So it works with SANS data out of the box. Here's another example where we have a dense reconstruction on the left of a DDM micelle, which has a strong negative contrast in the interior. You can see that here. I'm just coloring it. Green is positive and negative is red. And then if you take that same data and you attempt to do a bead model, it does not do a particularly good job. All right, here's some just examples of dense. Symmetry obviously helps a lot with reconstructing these. Here we have GROW-EL. You can see the nice cavity. This was a case with a DNA binding protein where you can actually see the small little hinge motion that they were able to model, and it improved the agreement with the atomic model and the scattering data. You can also, like I said, use this directly with SANS data. So this was a 5-fold symmetric ion channel generated with SANS data from the SAS-BDB. And not only can you see the nice symmetry, you can actually see these little holes in there at relatively high resolution, which was pretty neat. So it works pretty well. One of the things that density is great for is doing some 3D modeling. So dense returns what's called an MRC formatted electron density map, which is the standard format for cryo-EM reconstructions, which is great because any of the tools that have been built for cryo-EM can also directly be used with dense. And people have done this many times. You can do rigid body modeling of fragments or subunits or domains directly into the density. And because it's density, there's actually a gradient for the optimization routine. It actually can slide down the gradient and optimize the location and the position, which is something that you can't do with bead modeling. So here's just that example after they did that, and they were able to get a very good chi-squared agreement. They use, people have used Chimera. This one was using, I believe, Phoenix.doc and map. You can use CETUS or COOT even, and many other programs, which is great because there's been a ton of programs that have been developed for modeling into cryo-EM density. And then you can even then calculate a scattering profile right from that atomic model using Fox or Chrysol or something like that and get good chi-square values. One final note in terms of how we display density. It's a very important question. How do you display density? Because unlike beads, beads have a defined radius. So you just set that radius and that's what your envelope is. There's no question about it. With density, there actually is a question. Just like in crystallography, you scroll your mouse wheel up or down and in COOT or something, and it changes what your overall iso contour level is. And so if it's the same density, but it's just how you view it can affect your interpretation. And we found that typically when you're representing these things, something like 5 to 10 sigma is usually where you get the best match with simulations. So you can see the solvent accessible surface here in the mesh, and then 4 different RMSD values or 4 different sigma values. And so it may be that you're looking at some solvent shell out in the boundary here. I don't know. But typically for publications, you want to look at a variety of different sigma values, of isocontour values. So we have a website. There's a lot of great tutorial information on here if you want to download and install DENS directly. tdgrant.com/dens. We also have a web server. So if you want to try this, dens.ccr.buffalo.edu, you can go there and you wouldn't have to install DENS or anything. You just take your data, you upload it. It actually has its own little fitting program in there. So you can actually give it raw data and it'll attempt to fit that. I actually typically recommend you do that yourself because they're, the automated versions of these programs sometimes aren't the greatest. You can give it a genome.out file, which we'll use in a minute, or any other kind of smooth fitted data is really all you need to do. And it kind of acts like as a little GUI. You just run it in your browser. That membrane mode is available. You can use Symmetry. So that is available. It's even got a little interactive viewer. It takes about 20 to 30 minutes to run one of these. And you can actually view it right in your browser there. This is like you can rotate and interact with the map, which is really nice. And finally, dense MRC files are actually now accepted as formats in the SAS BDB. So if you do publish your results with dense, I strongly encourage you to actually go ahead and deposit your density maps, just like a bead model or something like that. And they'll actually display this in these nice 3D interactive density reconstructions right in the web page there. So that's really great that they do that. Okay, so just thanks to everybody that's helped me with dense, and now I think it would be a good time to maybe take some questions before we go on to the tutorial section. Does anybody have any questions about dense? Let me open up the chat in case somebody's got a chat question.
I had a question about the symmetry mode.
Sure.
Do you have support for like dihedral symmetry, or is it just only rotational symmetry about some axis?
Yeah, so we do have support for dihedral symmetry. So you can see this GROW-EL actually uses dihedral symmetry. The rest of these are rotational symmetry. I'm currently working on higher levels of symmetry. I know McCall emailed me the other day about spherical symmetry. I'm working on implementing that for you, McCall. But it's
thank you. That was my question.
Yeah. But right now it's cyclical and dihedral symmetry are available. But that's all for now.
Thanks.
But sorry, I don't really have a question, but I saw you show one of the example of the vesicle that have negative and positive densities. It's a really great tools. It's a great example that the bead modeling have a problem with this kind of particle. But in this case, I believe you needed to apply some symmetry or not at all.
No, this is ab initio. No, this is P1. No symmetry was applied.
Okay. Okay. Thank you.
Hey, Thomas, I had a quick question. In early days, we were very careful about fitting the P of R function instead of the scattering data. And I guess with your sort of shrink wrapping and the thinking about it as intensity on a detector doesn't quite fit, but you'd think that there'd be some way to tie it into the P of R as well.
Yeah, there is, and we are actually working on that. Effectively, it's using the Patterson function, which is the sort of real space equivalent of the intensity function in 3D. Like if you have a 3D intensity function that gives you a 1D scattering profile that's spherically averaged. If you have a 3D Patterson function, the spherical average of that gives you the P of R curve effectively, or the characteristic function, which is very similar. So we are working on that. There is a mathematical difference though, that we're trying to work our way through. But I actually do believe that will improve it. Theoretically, the same information is present in the P of R as is present in the scattering profile, but there's a bit more restraints, I guess you'd say, on the P of R curve, because it's sort of like you're doing like the equivalent of a one-dimensional solvent flattening in the P of R curve, and you're making it smooth so that it's regularized. But that information theoretically is also in the scattering profile that you give to dense, because dense uses that fit to the curve rather than the raw data. And that's sort of theoretically it's the same information, but I think there's sort of numerical considerations that could be helped by using the P of R curve directly.
Yeah, I mean, I think what happens, of course, is that, when we do apply a P of R function, we're already applying some kind of filtering, like human-based filtering. It has this Dmax. We're adding sort of getting rid of noise, you know, defining a Dmax, etc. Right? So,
Right. Yeah.
Yeah.
And as far as that's concerned, that is technically is what Dense uses, because so there's the raw data in the black dots here, but Dense actually uses the fit to the data, which theoretically that fit to the data has the same information. It has the Dmax information. It has all that regularization in it because it's just the Fourier transform of the P of R curve, right? So theoretically it's in there. But I think numerically there's some advantages, mostly because of how we're doing the gridding and the sampling and all that kind of stuff that would be helped by being able to directly use the P of R curve.
But to define your initial random density, you have a box of the size of the Dmax, and you define the Dmax from this GNOME output, or you don't have that restraint?
Yeah, so it's a good question. So minimally, according to information theory, the box needs to be at least 2 times the size of the particle, the Dmax of the particle. So if your particle is 100 angstroms, minimally, this box needs to be 200 angstroms on a side. Just to be safe, Dense actually starts with 3 times the size. So it's not super sensitive to Dmax. If you're off by Dmax by like 50% or something like that, it still does a very good job, and we do that on purpose.
Thank you.
Sure.
Can I have one question?
Sure.
Thank you, Thomas. It's very informative talk. Actually, I have a question regarding, like, in this dance model, how do you like place the atomic model into the dance model?
Yeah, we'll go through that in just a second. Actually, when we go through the tutorial with Raw, there's a whole way to do that. So Dense has some tools for doing the alignment with like a PDB file or with another density map. And so you can do that either in Chimera or you can do it directly with Dense. And actually Raw has that ability to use the Dense alignment for a PDB file with a density map right in Raw.
Thank you.
I see something in the chat as well. I had a question regarding how the program deals with flexibility. It seems that those regions will be low density. That's true. I don't know if I have it here. Do I have it here? I don't think I have it here, but it does deal with, do I have another one here? It does deal with density from solvent, or not from solvent, from disordered regions. So if you kind of take this, if you see, let me just blow this up here. So you can see, for example, this number 1 and number 10 here. There's actually some disordered regions, right? And similarly to bead modeling, it is able to actually reconstruct the density in that region. And the fact that it's sort of low density in between gives you some information about this and as to why it's flexible, right? There must be some kind of 2 flexible regions where one is globular and then a flexible linker connecting it to the main domain. Same thing down here. There was something like 20% of the residues were missing in the model itself. The other question is, have you tried lipid rafts with Dense? We've done nanodiscs. I don't know if that answers your question, but that's what you're seeing here, where you get a positive contrast on the outside, where your scaffold for the protein scaffold is for the nanodisc, and then on the interior this is sort of a cross section through from the top, and you can see the negative interior for that nanodisc, which you can see up here. That negative contrast really does a number to these scattering curves that really has to be accounted for. I'm not sure if lipid raft is the same thing as nanodisc, but maybe it's close enough. Okay, so if there's is there any other question before I go on?
Thomas, I had one question. Have you noticed any kind of size limit? How large have you done so far?
So believe it or not, I have not noticed a size limit. I actually simulated tryptophan and was able to reconstruct tryptophan with a hole in the thing, which was really great. So there's no minimum size limit. And I actually, with a collaborator, they were testing some stuff and they collected. So I've done viruses. Viruses are great. They work. But I also have actually done entire bacterial cells. We actually did Staphylococcus and what was the other one? Some other one. And one turned out with this rod-like shape and one turned out with this spherical shape, which is exactly what it was supposed to be. So far we've even done whole cells at this point, which tells me that there's really no size limit. I should take the Fourier transform of like a picture of myself or something and see what the SAXS reconstruction is, just to see what the limits are.
All right, that's great news. So 500 nanometers should be no problem.
Should be no problem. And that's one of the nice things is, and I didn't mention this, but it's an important point, is because it's density, dealing with solvent is implicit, right? Excluded volume is implicit to the nature of contrast. And the hydration shell is implicitly dealt with by the nature of density, which is the major limiting factor for why other algorithms that are modeling based algorithms can't do any size. For example, if you take like bead modeling, it doesn't really do much to model solvents. And so you can only use so much of the scattering curve. That's why when you go into raw or you use genome or something like that, it automatically cuts off your data because it can't use higher resolution information because it's got to explicitly model a solvent. So you can do that with like gas or something like that. But Densol deals with it implicitly. So it uses the whole scattering profile, which means since it's just Fourier transforms, it doesn't care what your particle size is. The only assumption that needs to be met is that solvent is flat. That's the only thing you really need for this to work.
Absolutely incredible. Thanks, Thomas.
Have you tried gram-negative bacteria? So there were like 6 different bacteria that they gave me. I don't remember all of them. I believe 1 or 2 of them were gram-negative. Don't quote me on that. I don't remember.
I think it might also be interesting if you have it to try Cryptococcus, because its capsule is so large. It might be interesting.
Streptococcus was one of them, and it gave capsules.
Well, I was talking about Cryptococcus, but
Cryptococcus.
Cryptococcus, it's a fungal pathogen. So.
Oh, okay, cool. Yeah, if you have data.
I'm thinking about this from the perspective of, they use mass spectrometry for some applications in terms of like trying to diagnose samples. And it would be interesting, that is the reason I asked about gram-negative bacteria, if there was something similar that could be done in a high throughput fashion with this. So
yeah, I mean, I think the big issue there is sample delivery. How do you deliver that particle and match, for example, like matching the beam size to the particle size? I think the experimental limitations become much more important there, since it's so atypical. You need to deal with ultra SAXS then, right? You have to get to these ultra low angles to be able to deal with that. In theory, there's no limit to the size, but I think in practice, the experimental limitations are far more limiting.
To comment on that, people do ultraSAXS on the whole bacteria, just figure it out, the membrane thickness, because they believe that when they're collecting ultraSAXS together with the SAXS data, they can figure it out, the changes on the membrane and the cell wall. But yeah, I will give you some data. I think I have a source for the ultraSAXS of the whole bacterial cells. It will be interesting to see the fluctuation in cytosol versus chromatin, what is inside, if that's possible, because there are features. There are features. It might be a
resolution limit, but sure, yeah.
There are features in both in ultraSAXS and SAXS region to see the fluctuation, but it's hard to interpret. So if there will be some very ab initio reconstruction, that would be really, really interesting to see if we can see something.
Yeah, that'd be great. I'd love to try it. All right, if there's no other questions, I'm going to bring up Ra here. So both, if you have ATSAS installed, Ra will allow you to run bead modeling and allow you to run dense. So if you have ATSAS installed, it'll run bead modeling. Even if you don't have ATSAS installed, you can run dense. You don't actually need to install dense, because dense being open source in Python, Jesse Hopkins, who develops Ra, he actually integrated dense directly into Ra. So it doesn't require a separate installation of Ra. The only downside of that is that any updates and bug fixes and things like that are only going to be available in the actual open source version of Dense until Jesse updates raw. So that's the only downside, but it's really great because you can get it to work right within raw. All right, so yesterday I believe you guys had a tutorial on how to use raw and how to generate a P of R curve. Is that correct? You're muted. You're muted, Mikhail.
I don't think we did a P of R function
We
from raw, but
Yeah, we just show that it's possible to do in raw. We have a couple of examples how to calculate Vignette and plot Kratky, but the real tutorials could happen later in afternoon. But it's okay. Go ahead.
Yeah, no problem. It's super fast. So if you open raw, I'm going to kind of go through this quickly, but all of these steps are on the raw website, very detailed. So grab some data. And then you just plot it, and then it'll pop up on the profile tab here. And then in this control panel, if you click on the profiles tab, you'll see your data, okay? And what you can do is if you right click on it, you can start doing some of these basic analyses like a Vignette fit, estimating molecular weight. And then there's two options here. One is BIFT and the other is genome. And those are both IFTs or indirect Fourier transforms. I'm working on, so I have one also in Dense. That's not part of raw yet because I just published it, but I'm working on integrating that into Dense as well, or integrating that into raw as well, so you'll be able to use that one. So we'll go ahead and use the ATSAS one, which is genome or GNOME, however you pronounce it. And that pops up this little window here. And it attempts to do a automatic estimation of Dmax. Really what you're looking for is this normalized residuals on the bottom here. You want this to be flat line, right? No severe structures or severe shapes. For example, if I make this like 50 for a Dmax, you notice this looks terrible, right? The fit doesn't look good. The residuals look terrible. And if I go up higher and higher and higher, eventually it gets to the point of getting closer, right? So we're looking at this P of R curve. You can see that it's driving it artificially to zero too fast. So we just keep going up until it looks like it's going to naturally go to zero, which is somewhere around 80 or so, right? And ultimately you want to see these normalized residuals to be flat. You can also give it a really big number, and what that'll do is it'll show you where it naturally wants to go to zero, and then you can pick that as well. So we'll set it at, I think it was 85 or something like that, right? So this is typically fine. If you're running DAMMIF or DAMMIN for bead modeling, you want to click this truncate for DAMMIF or DAMMIN because it'll chop off the last half of the data or something like that. That DAMMIF or DAMMIN can't use because it can't deal with the solvent. But if you're running Dense, don't check that. Dense can use all of it, right? And so that's just one recommendation. Okay, so you get your P of R curve, you've got a nice fit, and you click OK. So relatively straightforward. If you want to see that in raw, you can click the on this plot panel, you can click IFTs, and that'll show you the pair distribution function on the top and the fit to your data on the bottom. If on the left now that you've calculated that in your control panel, there's another panel that says IFTs. So click that, and that'll show you. I already ran this one, so it's still there. So if you if you look at this down at the bottom here, there's an electron density button. So you can actually just click that, and that'll launch the Dense window. All right. And then what you want to do is just go to this output directory and select a place to put it. I just made a folder and I called it Dense. Here I'm using from the SASBDB this SASDBT4, which is one of their benchmark data sets, but you're welcome to use whatever data file you want and just place it somewhere. And then I already ran this, so I'm not going to run it again. But what you want to do is then set the number of reconstructions, which defaults to 20. If you have multiple cores, you can actually run multiple runs simultaneously. I think I screwed something up on my settings, so it's not showing up, but you can run, however many cores you have. There's a few different options for the mode. If you want to do the default, it's slow. You can also run fast, but to be honest, it's pretty fast as it is. It only takes a few minutes for this to run. So I'd recommend slow. If you would like, you can also do membrane mode. Membrane mode, again, will allow you to reconstruct something with negative contrast, such as a membrane protein or a micelle or something like that. And then that's really all you have to do. Then you can have this box. You definitely want to check the box for aligning and averaging your densities. Whether or not you refine it is really up to you. By default, it's selected. It's not going to improve the quality of the map, but it will make it so that the final map that it gives you does have a scattering profile that matches your data, which the averaged one won't. Same thing with bead modeling. If you would like to apply symmetry, you can do that here. But note that this does not have dihedral symmetry. I think the latest version of RAW, this is an older version of RAW, I think the latest version of RAW does. But if you would like that, either download the latest version of RAW or you can install DENS directly. As I mentioned, you can actually also choose what symmetry axis you want. So X, Y, or Z just means long, middle, or short principal axes. So if you've got something that's elongated and you know that it is symmetrical about that long axis, for example, this, where's that glick thing that I had? For example, this guy here on the bottom left, or GrowEL, the axis is the long axis, right? If you look at the principal axes here, you'd have one along the length of this and then two coming out the sides. And the symmetry is about the long axis. So you can actually choose that. Whereas this guy on the right, the symmetry is actually about the short axis. So you'd choose the Z in that case, just so you know what that means. And then you can also align the output to a PDB if you'd like. I'd actually wait and not do that here and do that separately. So then you just click start and it'll run. I already ran it, so I'm not going to click that because it'll take a few minutes. All right, so that's how you run DENS. And I'm going to also show you, since it's very similar, how to run bead modeling, which I also ran. So again, you just click on the IFT, and when you right click on it, you have the option for bead model or electron density. So rather than clicking electron density, you would click bead modeling, okay? And that'll pop up this window. Mine was already run, so it's filled in with stuff, but yours will be blank here. Again, you select where you want it to go. Number of reconstructions, 10 or 15 is typical. Number of simultaneous runs. And then if you want to do the alignment and averaging, what modes you want to run it in, those kinds of things. Again, you just click start. It's very similar for DENS and DAMMIF. All right, and that'll run these different reconstructions in these different tabs, and then it'll do the averaging at the end, and it'll give you the results. All right. All right, so what we're going to do is we're going to view these. Okay, so I like to use Chimera to do this. Okay, so Chimera is a great tool for visualizing these things. You can also use Pymol, and you can also use Coop if you want to. But Chimera is great because there's some functional tools built into Chimera for doing things like model fitting and stuff like that. Okay, so the first thing we're going to do is load the bead model. Why don't we start with the bead? Actually, let's start with density, because I think density is a little bit easier to understand, and then we can take another minute to do with the bead model. So what you do is just go File, Open, and oh God, I'm somewhere else now. Sorry about that. You know what? It's already open on my thing. That's why. Yeah, here it is. Okay, so DENS will run and it'll generate this folder. And there's a whole bunch of stuff in this folder, right? So I ran it 20 times by default. And so it generates all these different maps. It does the enantiomer generation and selection. And it ultimately generates this average, right? So that's ultimately what we're interested in. It generates the average. It'll also estimate resolution for you. So you can look at this PNG file. I'll show you the resolution that'll show up in RAW. But what we're interested in is this average.mrc file. Okay, so if I load that into Chimera here, it looks like this. Okay, yours might be gray or something, but it looks like this. Now, one thing to note is sometimes when you do this, it'll look like some kind of crazy, it'll look something crazy like this, right? If you run DENS and you get something that looks like this, it just means that in your volume viewer, the threshold that it shows was way, way too low, and it's just showing noise. So just grab it and move it up even a tiny bit, and it'll start to change the density value, okay? If you run that, then you can also load in the atomic model, which in this case, it was a SAS BDB reconstruction. And so it's allowed us the ability to see the model that they generated, which was this fit model 1 thing, right? So we can load that in, and it's right there. So if we want to align these things, we can use a neat little tool in Chimera called Fit and Map. So if you go to the volume viewer, tools, Fit and Map, then this little window pops up on the bottom here, and it allows you to actually do a fit. So you select what you want to do. Like I already did this, so it's got a bunch up here. So let's just say this guy, and we're going to align it to the average.mrc file. And there's options in here if you want to use, for example, like correlation or something like that. We'll just use the PDB file directly. All right. So I like to make this a little bit transparent so I can see how well it's fitting. So I click the color editor and I just click the opacity. And now what I kind of want to do is first get it in the rough position. So if I deselect all the other models to be active, and then I can move this model around. Okay, so I kind of just need it in a rough idea of where it's sort of aligned, right? That's rough, right? And then maybe I want to rotate a little bit, make it look like it's there, something like that. And then we can come over here and we just click fit, and it just fits it. All right, now we get a nice fit. Alternatively, you can actually do this directly in dense or in raw. And there's an option here. If you go to, you guys can't see the top, but on the top of your file menu thing, if you click tools, it'll say electron density alignment. And it'll pop open this little dense alignment thing, and you can actually browse, select and browse to the PDB file you want to align to, and what your MRC, that average MRC file that you use is. So you can do that, and I think I already have that open over here. And that will allow you to do dense directly. So let me just open that. So you can see here the alignment that dense came up with. Okay, so the advantage of this is that it will actually do the enantiomer selection for you as well. And it's pretty quick. It only takes like 30 seconds, maybe a minute, something like that. So it's pretty quick. So you can see that the fit is pretty good. All right, so let's do the bead model. So let me turn these guys off.
Right.
And then if I go,
if I may, so let's just little comment on this. You mentioned enantiomer. I think we didn't talk about it a lot. So
okay.
If you say that the handedness is not present.
Sure. Yeah, so it's an important point that when you generate, I'm trying to think if I have a maybe this. So if you look at this, this is a particle that has a handedness to it, even at low resolution. So what happens is when dense reconstructs this, it's random which hand it chooses, right? So effectively half the time it'll choose the right hand, where you get this blob pointed in that direction, and the curvature of this thing is, this way. Whereas if you, in some other models, it'll be the opposite. So it'll be like the mirror image. And if you average all of those together without taking into account an enantiomer, you'll end up with something that's much flatter, like it'll average out the handedness of both. So what you have to do is actually test both hands and see which one fits better. So dense does that all during the averaging process. I'm sorry, I'm running a little behind, so I'm going to do this real quick. If you go to your results in DAMMIF, you'll see a whole bunch of stuff in here, right? From raw. The thing we're interested in is this damfilt.pdb. That's the sort of the final answer. So if you double click that, it'll show up in this weird ribbon looking thing, right? And this is not useful for our interpretation. And that's just because that's how Chimera does things by default. We can instead show it as spheres and hide the ribbon. Oops, show. And that gives you what the bead model is that Raw came up with for damming. Okay, and we can similarly do a fit. So the way we do a fit is kind of similar to how we do it with dense. So we use this fit and map tool. And if you click here and you click the bead model, the dammfil.pdb, what you can do is you can actually kind of generate a pseudo density map from a bead model. It's not real because it doesn't actually do that. It's uniform density. But what you can do is you can generate a map from this by just adding, calculating Gaussian atoms, and it adds them all up. So you click this little use map simulated from atoms and say a resolution of, I don't know, 10 angstroms or something like that. And you get this, which is a sort of the equivalent of a density map, but from your bead model, okay? And now you can again use the same tools to use that map to generate your fit to your model, okay? So that's pretty much it. Oops, wrong one. And then if I hide that, just make that transparent, you can see our bead model in there. And then if I just show our atomic model, that one, I don't know if it's that one. Whatever one I chose, maybe it's that one. I don't know where it is, but wherever it is, that's how you do it.
Yeah,
I don't want to take
yeah, thank you.
Yeah, but you can do it the same. You can do it the same way. Sorry that I went a little bit over there.
Oh no, Thomas, this was absolutely fabulous. Great. I think there will be questions, so we still recommend asking the questions. So if anybody has a question, please go ahead.
Yeah, I actually one question. Very nice talk. So when you were like showing that electron density thing, and you were fitting you were showing the threshold thing. What was that actually? How much threshold do you think should be used to visualize that thing?
So as I mentioned before, you typically want to use a threshold of around, I'm going to show the dense one here. You typically want to use a threshold around 5 to 10 RMSD. Oh, I know. So the way you do that, you can, for one, you can calculate that directly in Chimera. Chimera shows the values here as being, this guy is here. So Chimera shows these as actual electron density values, right? So 0.0195. If you go to tools, volume, mean, standard deviation, and RMS, then it'll pop up this little window, and you can look over here and it shows you what the RMS value is, which is 1 sigma, right? Or 1 RMSD. So if 0.0056, you just pop that in here, and now you can see, whoops, 0.0056, and now you can see what 1 sigma is. You can see 1 sigma is too big, right? But let's say it's, you know, 0.11 would be 2 sigma. Oops, 0.011 would be 2 sigma, right? And 0.022 would be 4 sigma. 0.044 would be 8 sigma. So you can kind of see, that's why I was saying somewhere between 5-ish and 7-ish sigma is usually a good estimate. So, but the idea is that when you're publishing this, you're going to have a few of them, right? You can go into PyMol. I've got on my website tutorials on how to get these nice colored volumetric maps. And you go in there and you set the sigmas that you want. You would set like 1, 5, 10, 20, something like that, or 1, 5, 7, 8, 10, or something like that. And as long as you put in the caption of your figure what sigma values you are, that's fine. That's exactly what they do in crystallography, right? This map is contoured at 1.5 sigma or something. This map is contoured, in this case, 8 sigma. So we typically have higher sigma values here in SAXS because it's lower resolution.
So, Thomas, I had a question on exactly this point. You know, I don't know whether RAW has an easy tool for extracting volume. And of course, that's assuming that the particle has equivalent density, uniform density. But I was wondering if you would recommend using the volume extracted from the SAXS curve to help you set this contour?
Yeah, so that's a good question. So you can do that. So if you go to I'm just going to show the ribbon there so we can see this a little bit better. So if you go to Tools in Chimera and measure volume and area, there's this little window that pops up, right? And so you can actually put what you want. So I'm going to do my aligned one here that I'm looking at. And you can see the volume is here 73,000 angstroms cubed. And as I raise, as I raise and lower my threshold, it changes the volume interactively, right? Which is really nice. So say if I look at this and it's okay, the volume of this from the Perot volume is supposed to be, you know, 120,000, then I can move this threshold until I get to 120,000. And then I know that's a good threshold. So that is another way to do it. The only issue with that are some of the assumptions that are made in the Perot volume estimation and in the errors of actually getting Perot volume. So I've tried this and sometimes it works and sometimes it doesn't. And usually it's just because of errors in the estimation of Perot volume directly from the scattering profile, because there's a lot of leeway there in how you do that. But yeah, so that is definitely another valid way of doing this. Does anybody else have any questions? I see another question in the chat. What are
There's
some?
a question for you as well. What are some fit parameters you pay attention to when you're using dense and DAMMIF to assess the quality of the fits?
Yeah, that's a good question. So why don't I show this? So when dense runs, if you just run like one reconstruction, and raw will show you all this, but I didn't have it here because it took too long. But there's a few things. So one, you can look at this fit.png file. Okay, and so this will show you the actual fit of the profile that dense reconstructed versus your experimental data. You can see the residuals on the bottom. Ultimately, what you're looking for is that it's sort of noisy and flat. That's an important one, particularly these lower Q ones are important. You can see that the residuals are very small here, so this is fine. Another one is to assess convergence. We can look at some statistics. So dense will calculate chi-squared as a function of step number, and that's shown in the purple one here. You can see that it starts way up here and then it falls pretty quickly and it kind of oscillates around and it does some things and eventually converges. What you're seeing here is it goes from large numbers to eventually equilibrating and converging at some value. So this convergence is important. So there's three values that it's looking at: chi-squared, radius of gyration, which is shown in this greenish, cyanish, aqua-colored curve, and then the support volume, which you remember we use shrink wrap, and that determines the volume of it determines the envelope. We can estimate the volume of that, or actually calculate the volume of that exactly, and we call that the support volume. That is not to be confused with the actual volume of the particle, because it will always be larger than the volume of the particle, because it's the volume of the region containing the particle. But it can be looked at as sort of an upper bound of your volume, but it's usually quite a bit larger than the volume. So as long as these are converging, that's a good sign. And then the fit of the reconstruction as well.
Thomas, can you change the binning?
The binning?
Yeah, of the spherical averaging or of the radial averaging?
Indirectly, you can. So when you run dense, there's some options in terms of what we call oversampling. So I mentioned that by default, the box size, if I go back to my my presentation here, the box size is typically starting at 3 times the size of the particle, right? If you go to a larger size, something like 5 times the size of the particle, then you'll have more shells and therefore you'll have more bins, right? So it's the same like maximum Q value because the voxel size is still the same.
Sure.
But then you get more sort of solvent that you're flattening. And so you get more bins. And so you can control it in that sense. Yeah.
Okay. Thank you.
but it's binned as minimally as possible. It's just one voxel per bin.
No, that's typically for speed, I imagine.
Yes, that's for speed. Yeah.
But if you don't care about speed, then it's okay to do this.
Yeah.
To expand it, increase
Yeah.
it.
So what happens is if you make the if you double the oversampling from 3 to 6, then what happens is it makes the box size twice as large, but then also all of your voxels will become twice as large. So if you want to compensate for that, then you need to increase the number of samples, which by default is 64. So then you would set it to be 128. And then it would take, it's not quite 8 times as long, but it's, quite a bit longer because Fourier transforms are like n log n or something like that.
Sure.
But it's at least 4 times as long, something like that. I feel like I'm way over my time here.